Okay, hi everybody, and thanks for everyone for joining, especially the students. I would like to acknowledge the University of Zhuhai for hosting this lecture. I would like to acknowledge the International Association of Mathematical Geoscience for organizing this event, and also the IAMG Award Committee for the prestigious award. My name is Dara Grana. I'm a professor of geophysics at the University of Wyoming. I'm appointed in the Department of Geology and Geophysics and also in the School of Energy Resources, where I'm the director of the Bayesian Learning Consortium. And today I'm going to talk about understanding mechanisms and properties in the subsurface, especially the spatial distribution of petrophysical properties using Bayesian learning. For the students who are not familiar with Bayesian learning. The idea of Bayesian is essentially a statistical way of interpreting mathematical modeling. And then learning means that we're going to try to understand something from the data and predict some properties in a statistical sense using the data that we acquire. And these data are typically geophysical data. So this is going to be the outline of the lecture. Um, First of all, I'm going to give you some background information about my career so that you know how I got to this point. And then we're going to talk about geophysical inverse problems, where we try to predict some properties from the geophysical data that we measure. And these properties are going to be mostly petrophysical properties, meaning porosity, mineral volumes, the fluid content of the rocks. We're going to discuss different probabilistic methods. There are different ways to solve geophysical inverse problems. So there are different ways to predict the properties that we care about from the data that we actually measure. But we're going to focus on the probabilistic methods where we can somehow quantify the uncertainty in the predictions of the models that we develop. And then I'm going to show you some examples in subsurface characterization. We're going to focus on some examples in oil and gas, some examples in CO2 sequestration, and some examples for critical zone or in general near surface geophysics. So let's start about myself. My background is in mathematics. I got my master's in mathematics in Italy, and then I didn't think I was smart enough or creative enough to do research in mathematics. I was really attracted by the academic career, but I was a little bit intimidated by how challenging it might be. So I decided to take a position as a researcher in the private sector. So I worked for 4 years in an oil company doing research on oil and gas, especially geophysical problems. Um, and during this time, I was working with the University of Stanford in California. The company had some research projects about pore pressure predictions. I was in charge of these projects. We collaborated with Stanford University for a couple of years, and then I decided to move to Stanford. I did my PhD in geophysics, and then I became a professor at the University of Wyoming in 2013, and I followed the usual path of the academic career in the United States, from assistant professor to associate professor, and I'm now a full professor at the university. So my research focuses mostly on petrophysical characterization of the subsurface. What this means is that I want to predict rock and fluid properties, for example, porosity, volumetric mineral fractions, fluid saturations, in the rocks that are underneath the subsurface. So in the subsurface. So I focused on three different problems: seismic characterization of hydrocarbon reservoirs. This was mostly in the first part of my career. And then I worked on seismic monitoring for CO2 problems. And then I finally moved to the geophysical imaging of the critical zone, which means mostly the near surface, subsurface, the first 30 meters or 100 feet. So the common theme in these applications is to improve the subsurface characterization using seismic data or geophysical data in general, and rock physics models. And we're going to see in this lecture how we can combine the data that we measure to the physics that we developed. But one of the key features of my research is that in addition to making predictions about the subsurface or building models, we also want to quantify the uncertainty in these models. And so we typically use geostatistical methods for developing these techniques to quantify uncertainty. So, what I would like you to learn today is how we can combine geostatistical simulations with geophysical data in order to make predictions of the spatial distribution of rock and fluid properties in the subsurface. So, the idea is that if we want to exploit something in the subsurface, either minerals, oil and gas, or if we want to study the feasibility of injections of CO2 and hydrogen or the displacement of groundwater, we need a 3D model where at each location, like, I mean, obviously we don't have continuous models, but if we discretize this 3D model in grid cells, say, I don't know, 10 meters by 10 meters, we would like to build a spatial model where at each location in each of these cells, we assign a value of the rock and fluid properties that we're interested in: porosity, permeability, fluid volumes, mineral volumes, and so on and so forth. So this process is often referred to as geostatistical inversion. Geostatistical because we start with a set of geostatistical simulations, and then inversion because we update them or optimize them based on the geophysical data that we actually measure. And so the key problem here is the geophysical inverse problem. We measure a set of data and we want to predict some rock and fluid properties that we know affect the geophysical response, but we don't know what they are. So if we knew what the properties were, then we could actually compute the geophysical response. Now we measure the geophysical response and somehow we have to go back. So this is something that happens all the time in earth sciences. We want to, especially when we study the subsurface, we want to build a model of some variables because they change laterally and sometimes also in time. So we want to build a model of these variables, but we can only measure some indirect properties. So, for example, if we're interested in oil and gas, we typically care about the porosity, the permeability, the fluid volumes, but we cannot measure these properties directly in the subsurface. What we can measure is generally seismic data, sometimes electromagnetic data. We know that seismic data, the seismic response depends on the spatial distribution of the properties that we care about, but we cannot measure these properties. We can only measure the seismic response. That's pretty much the same in groundwater. We're interested in understanding the flow paths in the subsurface. So we know that when we have rainfalls, the water infiltrates in the rocks and then it moves through the rocks. For example, if we're looking at a mountain watershed, it's going to flow to the valley. Well, we would like to be able to map this fluid paths where the water goes, but we cannot measure directly the concentration or the volume of water at all the locations. We might have some boreholes, but typically we cannot measure exhaustively the spatial distribution of the water saturation variable. What we can measure is, for example, electrical data, and then we can take the electrical data and convert them into the water saturation. In mining, it's a similar problem. We want to predict the mineral grades and we measure the seismic data. So all these problems, they have something in common. Um, there are some variables that we care about, the variables of interest, the ones in red, and there are some data that we can measure that we know they're related to the variables of interest because we know somehow the physics, but they're not direct measurements. So these are the variables in blue. So the actual measured data. So what we can do is formulate what we call an inverse problem. So we know that the data depend through a function f, which is essentially the physics. The data depend on the variables of interest, and then there's always an error, which is the error in the measurements. Now, if we knew the variables of interest are, we could compute the data D, but we don't know the R. What we know is D, so we have to solve an inverse problem because now we want to explicit R as a function of D. We call it inverse because the physics goes from the red variables to the blue variables. Now we measure the blue variables and we want to go back. So this is going to be the problem that we try to solve today. We want to estimate rock and fluid properties from a set of geophysical measurements. But remember that the key is going to be to quantify the uncertainty, and this is why we're going to introduce Bayesian methods, or in general, probabilistic methods. So the idea, once again, is that rock and fluid properties cannot be directly measured in the subsurface. What we can measure is geophysical data. So we build this kind of inverse problem. Assume that the variable of interest, for example, is porosity. Well, if we knew the porosity in the subsurface, we could compute the theoretical seismic response that we would measure if we were doing, for example, a seismic acquisition. Now, we don't know the porosity. What we know is the seismic data. So now we have to estimate the porosity from the seismic data. So essentially, the physics goes from the right, from porosity, to the left, to the seismic data. And now we measure the seismic data. We don't know the porosity. This is why we call it a geophysical inverse problem. So what are the properties that we care about in the applications that I told you before? Well, in general, we care about the pore volume, especially if we're interested in estimating the fluid volume or the fluid pass. We care about the pore volume because we can quantify the amount of fluid in the subsurface. Then we care about the mineral volumes, different minerals or the rock types in general. Different rock types, they have different geophysical responses. For example, limestone is stiffer than sandstone, so the velocity of the seismic waves is going to be higher, and so on and so forth. And then we care about the fluid volumes. For example, in oil and gas, you might have gas, you might have oil, you might have water, and so we have to understand the percentage of these fluids in the pore space. Now, these are not the properties that these properties cannot be measured directly except from a few locations, for example, the boreholes. What we can measure is typically geophysical data. So seismic data, electromagnetic data, gravity data, and so on and so forth. So this is an example of a seismic data set. So at each location, every 25 meters by 25 meters laterally, we acquired some seismograms, essentially, some seismic traces by putting a source and a bunch of receivers. And now we collected them in a 3D volume. This one here is probably something like 500,000 traces. And then we just interpolate to make it look like a continuous signal. Of course, it is discrete. But when we put it together, we can see that there are some anomalies, and these anomalies, they're generally an indicator of potential changes in the subsurface, for example, from one rock type to another rock type, from a rock type that is not permeable to a rock type that is permeable, or from one fluid to another fluid. So here, for example, it seems that we might see an anticline, which could be potentially an oil and gas trap. Today, I'm going to mostly talk about seismic data. Most of the research that we develop in terms of mathematical methods can be applied to multiple geophysical data sets, and we're going to look at the end at one inversion where we include both seismic and electrical data, as long as you know the physics. So for these types of geophysical data sets, we typically know the physics that link the geophysical properties to the actual measurements. And then we use rock physics to convert the geophysical properties into the rock and fluid properties that we care about. So typically with seismic data, we can predict the velocity of the seismic waves. And then from the velocity of the seismic waves, we can predict the rock and fluid properties. For electromagnetic data, we can predict the resistivity, and then from the resistivity, we can predict the fluid saturations. Gravity, we can predict, for example, the density that depends both on porosity and fluid volumes. So again, just to recap, these are the properties that we care about: the porosity, the water saturation, the clay volume. And these are the data that we typically measure. And today we're going to, in the first part of the talk, or for most of the talk, we're going to focus on seismic data. Now, when you try to solve an inverse problem, you need to know the physics. So we need to be able to go from right to left if we want to do the inversion to go from left to right. So the physics here, especially in the seismic inversion problem, is combines rock physics, which basically means pore elasticity. We're going to look at some of the rock physics models in a minute, since I assume that some of you might not be familiar with it, and then seismic wave propagation, which is essentially the same physical theory that controls propagation of earthquakes, and so on and so forth. So we know what properties we want to estimate. We know what we can measure, in this case, seismic data, and we know the physics that links the properties of interest to the data. So what we have to do is to put everything together with some mathematical inverse theory in order to make predictions of the properties that we care from the data that we measure. So let me talk a little bit about rock physics. So we're going to talk a little bit about the physics, and then we move into the inverse problem, or the mathematical methods that are used to solve the inverse problem. So this is how I generally envision a porous rock. So here we have a representative elementary volume. This is supposed to represent the granular media. So we have different grains with different sizes. So you can imagine, for example, that the yellow ones are the big grains, for example, quartz, and then the small ones are the small grains, for example, clay. So here we have a mixture of two different minerals, and then we can have multiple fluids. Now here I made it look like there's gas in the top and water at the bottom. Sometimes the mixture is a little bit more complicated. There might be some capillary forces that create mixtures of say 15% of water and 85% of gas. But that's the general idea. We have a solid phase where we have some empty pores, some empty space within it. This is what we call the porosity. And then within the pore space, we might have different fluids. Generally, in the subsurface, we don't find vacuum. We don't find empty pore space. There's always a fluid near the surface. It might be air. In the deeper subsurface, it might be oil, water, gas, CO2, or hydrogen, depending on if we're extracting resources or if we're injecting. Um, so yeah, this is the cartoon. So we have a solid phase. Here we have two different volumes, clay and quartz, and here we have two different fluids. It could be oil and gas, it could be water, and so on and so forth. And in rock physics, so the geophysical response that we measure at the surface depends on the volumes of the solid phase and the fluid, but also on the way solid and fluid are arranged. So rock physicists develop two main ways to idealize the geometry. So these are two different conceptual models. Here on the left, we have granular media. In granular media, we use spheres to mimic the shape of the grains. So for example, here we have bigger, well, in this case, it's a 2D cartoon, so it's a circle, but imagine it in 3D where we have a sphere, larger spheres here represent the quartz grains and smaller spheres, the clay grains. And then whatever is left is the pore space where the fluid can flow through. The other option is instead of modeling the grains or the solid phase, we model the pore space directly. So if you think about rocks like limestone, rocks that are really stiff, for example, we don't have a grain structure. We have a coherent solid phase, and then in within we have some fractures, like small fractures that are typically connected between each other. So the idea is that we model these fractures or these cracks, if you want to call them, like ellipsoids. Like here, they are randomly oriented. There might be a preferential orientation in some cases, but it is that we have these ellipsoids in 3D that are connected within each other, and then the fluid flows through these cracks. So here on the left, we have a theory which is based on granular media. Here on the right, it's a conceptual model that is based on inclusion. So these are two big families of models that we're developing rock physics. So for each of them, as long as you know the porosity, as long as you know the fluid volumes, the mineral fractions, the shape, like the size of the spheres or how elongated the pores are, as long as you know these properties, you can compute, for example, the velocities of the seismic waves that propagate through this media, and then from the velocities you can compute the seismic response. So these are obviously simplifications because the rocks are much more complicated than this, but these simplifications are really useful to build some rock physics models that can predict the elastic behavior of the porous rocks. So here there's an example. So on the x-axis, I plotted the porosity. On the y-axis, the p-wave velocity. So if porosity goes up, then the p-wave velocity typically goes down. So these are two different granular media models. One is the solid line is for rocks that are unconsolidated, almost similar to the sand that you find at the beach, where you don't really have a coherent structure, like the grains are kind of loose. And then the dashed line is for stiffer rocks that are more compacted. So they generally show higher velocities because of the higher stiffness. So the general idea, though, is that if porosity goes up, it means that there's more fluid and less solid. The fluid is more compressible, which means less stiff, which means that the elastic velocities will be, the seismic velocities will be lower. So for example, here, the P-wave velocity decreases almost linearly for stiff rocks. It decreases more rapidly for soft rocks. Anyway, these are theoretical models. Now I'm going to show you an example where we actually see if these rock physics models, they actually work. So this is an example where from a data set in Wyoming, this is the Rock Springs Uplift, which is a potential CO2 storage site in the state of Wyoming. And here we have some samples where we measure in the borehole the porosity and the velocity of the seismic waves. We have different rock types. These green diamonds are dolomite. Dolomite are really stiff. They have more the structure of a fracture rock. So here we used inclusion media, and you can see that they pretty much follow almost a linear trend. And then here in yellow, we have some sandstones. This sand, the porosity in this specific sandstone layer is relatively low. The average is approximately 0.6, 0.7. The maximum value is 0.12. So we only have the sandstone for a small porosity range, but we can see that kind of rapid decrease that we were talking about before. So here we have two different rock types, so we have to develop two different rock physics models. So we talked about rock physics, and now let's talk briefly about seismic wave propagation. We said that the physical models combine rock physics because from the petrophysical, from rock and fluid properties, you can compute the velocities, and then you have to compute the seismic response, right? We don't measure velocities at the surface. What we measure is a seismogram. So the idea is that we have a source, for example, this one here in red. Think about a small charge of dynamite, or think about a student hitting the rock with a hammer. And then here we have a bunch of receivers, the blue triangles. Now we propagate some seismic waves. The seismic waves that propagate through the surface, at some point they find an interface between, for example, the softer rock and the stiffer rock. So part of the wave is reflected back to the surface and part of the wave is transmitted. So each receiver is going to record this kind of anomalies, like a seismogram when there is an earthquake. So here we have, for example, a flat signal because at this point the wave is propagating through an homogeneous medium. And so at some point it's going to find this interface here. So there's going to be a reflection. So we record this anomaly. And every time we see this kind of anomalies, it means that there's a change in the subsurface. So there might be something interesting there. For example, water, oil and gas, CO2, and so on and so forth. Or maybe just a lithological change, just different layering. So if we want to learn about the structure of the subsurface, these are really useful information. So here there's an example of how the seismic data looks like. So essentially what I did is just take, oops, sorry about that. I just took all these seismic signals for this location here, and I put them together in a coherent signal, and then I moved the source, and I kept doing this procedure, say every 25 meters in the horizontal direction. And now what I get is that I have a bunch of seismograms. I'm going to just interpolate them. So every time you have a peak, you're going to see, for example, a blue color or well, in this case, it would be a minimum. And then when you have a peak, is going to be a red color. So here we have three seismic sections from a data set in Norway. This is the Norne data set, which is in public domain. And then what you see here is that at some point there are some anomalies. This anomalies here tells you that there is something in the subsurface. It's most likely a contrast between two layers, but one of the layers might have, for example, some fluid. For in this case, this is an oil and gas study, so there might be either oil or gas, because we recorded a change in the seismic response, which means a change in the elastic properties. So again, let's recap. So now that we look at the physics, let's recap what we want to do. We want to estimate the petrophysical properties in the subsurface. So for example, porosity and the volume of the fluid. So these are the unknown properties. And what we measure is, in this case, seismic data. So we measure some kind of signal that depend on the elastic properties. Oh, sorry, on the rock and fluid properties. So this is the inverse problem that we're trying to solve. We estimate rock and fluid properties from geophysical data. And again, remember that one of the goals is going to be to quantify the uncertainty. So why am I stressing so much on the uncertainty? Well, the idea is that the solution of the inverse problem is uncertain. Like you're not going to come up with a single model that you're 100% certain that is going to be the solution of that is going to be the true model. What you're going to be able to do is to come up with a set of models or some kind of probability distribution that tells you something about the uncertainty in the subsurface. The reason why we cannot come up with a single deterministic model is that there are several sources of uncertainty in the problem that we're looking at. There are some approximation in the physical models. If you think about my rock physics models that I showed you before, there are clearly some approximations there. You know that grains are not spheres. They generally have a much more complicated shape. You know the pores are not ellipsoid. Again, they have a more complicated shape. So the idea here is that all the models, all the physical models that we use, they're not perfect. They're approximations because we really don't know all the details of the pore-elastic processes that happen in the subsurface. The resolution of the data is also a source of uncertainty. The data, they're measured at the surface, sometimes for targets that are 2,000 meters deep in the subsurface. So these data do not have an infinite resolution. They somehow average layers in the subsurface. For example, typically the resolution of seismic data is 10 to 20 meters. Electromagnetic data, the deeper you go, the smaller the resolution, and so on and so forth. Then there is some noise in the data. If you look at the signals that we record with the geophones, with the seismic sensors that I showed you before in the previous slides, well, you don't really have a flat line when you're traveling in an homogeneous medium. You have some kind of noise. This noise is also a source of uncertainty. And then finally, there is natural variability and heterogeneity. If you think about our models, we typically discretize the subsurface, say, if you're lucky, like 10 meters by 10 meters laterally and maybe 1 meter vertically. Well, if you look at a core sample and you look at the variability of the shape of the pores or the shape of the grains, well, there's a lot of variability even just in a core sample. Imagine when you try to average the properties of different core samples in a cell that is 10 by 10 by 1 meter. So there's clearly there are several sources of uncertainty, and so the impact on what we're doing is that the solution of the inverse problem is uncertain. For example, here I calculated two different maps of porosity. This is the top surface of the reservoir in the North Sea, and these two these two models, they match the seismic data equally well. But if you look at the realization on the right, the porosity is much higher than the realization on the left. Well, actually, it's not much higher, but you can clearly see that there is more red. So there are more cells with high porosity in the model number two than in the model number one. Yet these two models, they actually match the seismic data equally well. And in this case, I actually built 100 different models that match the data equally well. And again, they were all slightly different because of all the sources of uncertainty that we talked about. So now that we set the problem. So the problem is predicting rock and fluid properties from geophysical data, specifically seismic data in this talk, knowing the physics that controls the physical relation between rock and fluid properties and geophysical data. So now that we know what the problem is, and we assume that we know the physics or some kind of approximation of it, we have to solve the inverse problem. Now, there are different ways for solving inverse problems. You can use either deterministic methods or probabilistic methods. Now, most of the probabilistic methods, they are somehow Bayesian methods, and we're going to talk about the Bayesian method in a minute. I'm going to focus on probabilistic methods for several reasons. Mostly because I think that the probabilistic framework is ideal for problems where we want to quantify the uncertainty, because we can come up with a probability distribution or some sort of measurement of the uncertainty in the model predictions. And so we can come up with either probability distributions or a set of model realizations that tells you something about the variability of the model. So here is a little bit an introduction to Bayesian inverse problems for those of you who are not familiar. The idea is that in the Bayesian inverse problem, excuse me, we have a prior distribution. So we have some kind of prior information about the model that we want to build. For example, if you're studying porosity, you know that typically porosity in the subsurface is between 0 and 0.4, like 40%. You never have in the subsurface rocks with more than 40, 50% of porosity, for the simple reason that the weight of the sediments above will compact the rocks in the subsurface and reduce the porosity. Or if you're studying, for example, the velocity of the seismic waves, typically the velocity of the seismic waves, well, it's a positive value, and then it's typically between, well, greater than 0 and less than 7 kilometers per second, maybe 8 kilometers per second maximum. So you have some kind of a range, and you also know that the most likely values are around 2, 4 kilometers per second, depending on the target that you're looking at. So you can actually come up with some kind of prior distribution that model your prior knowledge about the variable that you care about. So this is essentially what we know about the subsurface before we make any measurements. And then we make some measurements. And so we have what we call the likelihood function or the likelihood model. The likelihood model links the data that we measure to the model properties that we care about. So essentially, it's where the physics comes in. You know the relationship between model and data, because if you knew the model, you could actually compute the predicted data. And then we have to combine the prior and the likelihood. And so what we get is the posterior distribution. And we do it using the Bayes theorem, which basically says that the probability of the data given the model, which is the likelihood, times the probability of the model, which is the prior distribution, divided by the probability of the data, which is just a normalizing constant, gives you the posterior probability of the model given the data. And if we're lucky enough, if the data are informative, we're going to reduce the uncertainty in our prior model and get more accurate predictions of the model variables that we care about. So here there's an example. We have 3 seismic traces measured at the same location, just with a different geometry or a different distance between the source and the receiver. This is a synthetic data set. So here we have some big anomalies at the top. Then there's not too much going on in the middle, and then some bigger anomalies at the bottom. So here a geologist might say, well, here at this time, so seismic data are recorded in time, for those of you who are not familiar with seismic data, but here there's something going on, there's a clear anomaly. So this could be, if we're looking at an hydrocarbon reservoir, this could be, for example, the top of the reservoir. And here there's again something going on, so this might be the bottom of the reservoir. And then some experts in seismology could tell you something about this one here looks more like noise, this one here is more a coherent signal, and so on and so forth. But the idea is that we have this kind of data, and we want to predict, in this case, porosity, the volume of clay, and the water saturation. We chose these 3 properties here based on the prior geological knowledge that we have in the field. So the result is this one here. So first of all, let's just look at it in a deterministic way. Let's just look at the prediction that we get from our models, and then we're going to talk about the uncertainty part. So the prediction is the red line, and here, since it was the seismic data were measured near a well, we actually could compare the predictions to the actual measurements in the well, and this is the black line. So here at the top, let's just focus on porosity. Here at the top, we have a high porosity, then it goes a little bit lower, and then it increases again. And then it goes again a little bit lower, and we have a pretty good match with the actual measurements, especially in the top. And then here it seems that we're not really able to predict correctly some of these variations, abrupt variations in thin layers. And then let's just look at the water saturation. Here the water saturation goes down, so this is an oil field, so here it means that there's oil, and then the water saturation goes up again. What happens based on the clay content is that there's some thin layer of clay that separates the reservoir at the top from the reservoir at the bottom. Here again, we have some low water saturation, which means that high oil saturation, and then we go into water saturation equal 1. So if you are a geologist or an expert in interpretation of petrophysical data, properties, you could see that there's a reservoir a potential reservoir at the top, and then there's a thin layer of clay that separates the two reservoirs, another reservoir here, which is probably the main target for the company. And then here, there's nothing going on. We enter into the water table. Anyway, so this is how a deterministic prediction would look like. We have some data, we predict a property, we compare it with the true one just to make sure that if we have it, just to make sure that there's a good match. But in this case, we're actually doing a probabilistic inversion, so we have some kind of measurement of the uncertainty. Now here I did it in two different ways. First of all, I used the Bayesian inversion with an analytical solution where using some approximations, we come up with the actual posterior distribution of the petrophysical properties. And this is the background color here that goes from low probability, probability close to 0, which is the white part of the color bar. Then blue is low probability, and then yellow is high probability. So if we look, for example, at porosity, it seems that we have high probability near the red line. And then the further we get from the red line, then we get low probability. Well, the red line is the most likely value, so the red line should actually mark all the points where the probability is the highest for each location. Then I did it in a different way. Instead of trying to estimate analytically the posterior probability distribution, what I did is I created a set of realizations, and then I condition or updated the realizations using the data that we measured. So if you look carefully in this plot, you can see a bunch of gray lines. Here we have 500 different models that were actually updated or optimized using the data. And now you can see that all these gray lines, they tend to match the probability distributions, the background color that I showed you before. I'm going to show you these two different methods specifically in a minute, so I'm going to go into the details of the methods pretty soon. But I just wanted to give you an idea of what a probabilistic inversion looks like. In this case, a seismic inversion. So we have seismic data. We want to estimate reservoir properties, meaning in this case, porosity, clay volume, and water saturation. And we have different stochastic methods or statistical methods to estimate either the probability distribution or a set of realizations that mimic the probability distribution. So in the next 10-15 minutes, I'm going to go through different probabilistic methods. I'm going to start with Bayesian analytical methods. In this case, what the goal is to try to estimate analytically the posterior distribution. So imagine the posterior distribution as the typical Gaussian distribution, the bell shape. So we would like to analytically compute with some mathematical formulation the mean and the standard deviation or the variance of the Gaussian distribution. And if we have multiple properties, we're going to estimate the covariance matrix as well. Then we have stochastic optimization methods. The idea of stochastic optimization is that we create a set of realizations and then we update these realizations or optimize their realizations based on the data that we measure. Then we have Monte Carlo methods where we essentially randomly generate a set of models, a set of realizations, and then we accept them, or instead of optimize them, we accept them or reject them based on how well they match the seismic data. And then I'm not going to talk about machine learning and deep learning because this would require another lecture, but there are some data science methods or AI methods, mostly machine learning and deep learning, where you can actually solve the geophysical inverse problems and you can also quantify the uncertainty. This is something that my research group started to work on in the last couple of years, especially Ming Liang Liu, my PhD student who then went to Stanford as a researcher, and he's now a full professor at University of Shandong. And then Peng Li, who was also a PhD student in my group, who is now working at Stanford University as a postdoc. So let's start with Bayesian analytical methods. So the milestone in Bayesian seismic inversion is the paper by Bull and Anomer in 2003, which is a Bayesian linearized AVO inversion. So essentially what they did is they linearized the seismic model, the forum model. So the forum model is relatively complex, but you can approximate the model using a convolution and a linearized approximation of the reflection coefficient. So we take the equation for the reflection coefficients, which is not linear. We linearize it. So the equation for the reflection coefficients compute the reflection coefficients at the interfaces based on the elastic properties, so velocity and density typically. This equation is not linear. This is represented by Zoepert's equations, but it could be linearized using some approximations, for example, Aki-Richard, Shui, and so on and so forth. Now, there are some limitations to apply this approximation, but if these if these assumptions are met, then the linearization is generally relatively accurate. And then the novelty in the work of Bull and Anomer is that they take a Gaussian distribution of the logarithm of the elastic properties, and combined with the linearization of the model, they come up with an analytical posterior distribution of the elastic properties. So there are some key elements that are not simple to implement, but essentially, if you're assuming that the logarithm of the elastic properties is Gaussian, it means that the elastic properties are log normal. And because the linearization of the seismic model is expressed in the logarithm of the elastic properties, you simply assume that the logarithm of the elastic properties is Gaussian, then it's a linear inverse problem. You can compute it analytically. I simplified a little bit. If you're interested in the math, essentially, we're saying if the model variables that we care about, the logarithm of the elastic properties is Gaussian, and if the error is Gaussian, with zero mean, non-covariance matrix, and independent of the model, and if the model, the forum model is linear, so you can associate a matrix to the linear model, then the posterior distribution of the model given the data, so the logarithm of the elastic properties given the seismic data, then it's also going to be Gaussian, and you can find an analytical formulation for the mean and the covariance matrix. So this means that every time you have, remember when I talked about the seismic data and they said, well, every 25 meters you have a seismic trace, like that kind of seismogram that looks like we had an earthquake. Well, at that point, it means that for each of the trace, at each location in the trace, you apply these two equations here. So in MATLAB, it would be just a for loop over all the traces, and then just two equations in the for loop, so relatively simple. Then you can analytically compute the posterior distribution. So let's just look at an example. So here we have so on the left, we have the application to the well logs. So this is a 1D signal, and on the right, it's the application to a 2D section. So we have a 2D map. So on the left, you have the true model is the black line. At the well location, you can measure everything you want almost. So the well location is actually a good place to validate your model. So the black lines here are the well log data. So here they just block them every 4 milliseconds, I think, or sorry, maybe it's 2. But anyway, and then in blue, you get your estimate, or in cyan, I guess. So the solid thick line is the most likely model. And then you see that there are some two thinner lines. These are the upper and lower bound of the confidence interval. In this case, they chose the 0.95 or 95% confidence interval. So this is the upper and lower bound of the interval. And most of the true data, they actually fall within that interval, except this layer here. So here it means that either there's something wrong in the inversion, or maybe the data do not have enough resolution to capture that abrupt change that is only probably 1 or 2 meters. So now we do it for all the possible traces. Now we can only validate the well location where we have the data, but we can do it for all the possible traces. And then we just interpolate, get a continuous map. And here there's the map of the reservoir. So here you see some pretty much constant velocities. And then all of a sudden you have this anomaly here with some high velocity. Here there's something going on. And this well is right here, so we can use this well to validate. Same for density. So here we have P wave velocity and that's wave velocity. So they're just velocities propagating in orthogonal directions of motions. And then here you have the density. So again, there's a density anomaly. There's something going on there. So this is how I started my career. So the paper of Boole and Nomre was published in 2003. I started my career as a geophysicist in 2006. So some of the contributions that I made to this field is that I try to combine the Bayesian linearized AVO inversion with rock physics, so that in addition to estimating to estimate P wave velocity as wave velocity and density, we could also estimate rock and fluid properties, for example, porosity, volumes of the minerals, fluid saturations, and so on and so forth. So essentially, I did a seismic inversion, but the parameterization of the model is in terms of rock and fluid properties, for example, porosity and water saturation, instead of elastic properties, P wave velocity and density. One of the key features is that the seismic forum model is the same no matter what rock type you have. You might have different velocities, but the propagation of the physics of the propagation of the seismic waves is the same. However, the rock physics part, so the pore elastic model, is different depending on different rock types. I showed you before. If you have a granular media, you're going to have grains, and you use certain equations. And if you have fractured rocks, then you have then you can use inclusion models where you model the shape of the pores. So because of this difference, because of this different elastic behavior of different rock types, the distribution of the petrophysical properties is typically not Gaussian. You don't have a bell shape where most of the values are around a specific value, the mean, and then you have some spread around the mean, which is the variance. You have multimodal distribution. So each rock type might have its own Gaussian distribution with specific parameters. And then when you combine them together in a sequence of different layers, you're going to get multimodal distributions. That was the second contribution in my research. So in 2010, we published a paper with Ernesto de la Rosa, where we develop a seismic petrophysical inversion, so combining seismic and rock physics to predict rock and fluid properties, where we develop a linearized rock physics model and combine it with Gaussian mixture models. Gaussian mixture means mixtures of different Gaussian distributions with different parameters. And then we further developed this model by working with Henning Omre's team at University of Trondheim, NTNU in Trondheim, where we combine Gaussian mixture model with Markov models with a linearized rock physics model. So here the idea is that in addition of predicting the spatial distribution of the petrophysical properties, we would also predict the rock type. So we would be able to tell which rock type we have and what the petrophysical properties in these rock types are. So here there's an example. This is the PhD project of my former student, Xiaojiang Lang, who is now working in data science in the Bay Area. So that's exactly the same example that I showed you before for Boole and Nomre. Here, there's the validation at the well location. Again, the black lines are the true values, and then the red lines represent the most likely value and the confidence interval. And then we did the same along the section and then interpreted the results. So here you can see some anomalies of porosity. This means that you have high porosity, potentially you might have hydrocarbon, and then here you have water saturation. So here we are in the water table, but at the top you can see that there is some low water saturation, which potentially means oil and gas. In this case, it was oil. Okay, so that's enough for the Bayesian analytical part. So the idea of the Bayesian analytical part is that you have a seismic inverse problem, and you want to predict analytically the posterior distribution of the properties of interest, either elastic or petrophysical properties, conditioned by the data. Now, in order to solve this problem using Bayesian analytical methods, you have to make some assumptions. You have to assume that the rock and fluid properties are Gaussian distributed. You have to assume that the model can be linearized. What if you don't want to make these assumptions? Because, for example, the model is not linear, or the rock and fluid properties are not Gaussian. Well, in this case, we can use stochastic optimization methods, and there are a lot of methods in this subgroup, but the idea is always the same. Somehow we generate a bunch of models, either all together or sequentially, but the idea is that we can use some geostatistical techniques like probability field simulation, sequential Gaussian simulation, multi-point geostatistics to build a large set of models. For example, an ensemble of 1,000 models, 3D models of the subsurface, or 2D, or whatever your problem requires. Then we need a Fora model. So for example, in the problem that I have been discussing so far, it's rock physics combined with seismic wave propagation. So we take all the realizations that we look at, that we created in the first step, we apply the Fora model to compute some predictions of what the theoretical geophysical response would look like. And then finally, we apply a stochastic optimization method in order to update those realizations until they actually match the true data. So if you simply generate geostatistical realizations and apply your Fora model, and you're going to compute a theoretical response of what the seismogram would look like, and you compare with the true one, it's clearly not going to match unless you're really, really lucky, but you have to be really, really lucky. So what you have to do is to do some stochastic optimization. So you perturb your initial realizations until the model, the theoretical model that you come up with, actually match what you measure in the field. And for stochastic optimization, you can use ensemble-based methods, simulating annealing, MCMC methods, probability perturbation, genetic algorithms, and so on and so forth. So there are different families of methods that you can use for stochastic optimization. Today, we're just going to look at one, which is the ensemble smoother multiple data simulation that was developed by Emmerich and Reynolds in 2013. This is one of the most cited papers in computers and geosciences. In the same way, the paper by Bullen and Ombre is one of the most cited papers in geophysics. So the idea of the ensemble smoother is you generate an ensemble of realizations. For example, 100 realizations of the 3D volume of porosity. And then you have some data that you measured, and then you compute the theoretical response using your Fora model, for example, the seismic, and then you update the ensemble of models using the ensemble smoother multi-data simulation technique, which is essentially this equation here with some caveats. And then you repeat this prediction updating step several times until your data actually match, until your models, the response of your models match the data that you measure. So here there's an example. This is the PhD thesis of Min-Yang Liu. He published this paper in 2018. He's now a professor at University of Shandong. So here he generated 500 different models for porosity, clay volume, and water saturation. Now, the true one is the well log, but we pretend that we don't know the true one. That's the one that we want to predict, right? So the red one is just one of the 500 realizations, just to show you how it looks like. It doesn't match the blue one, of course, because it was created randomly based on some prior knowledge. For example, we knew that the porosity was between 10 and 30%, just based on some measurements. We knew that the water saturation was higher at the top than at the bottom, and just because of gravity, and so on and so forth. Sorry, the water saturation was lower at the top than at the bottom because of gravity, and so on and so forth. But for example, there are features that we didn't know. For example, we didn't know that there was this clay layer here. We didn't look at the well log data. What we did is generate 500 models. The red one is one of these models. It doesn't match the blue one, but somehow it has some similar features, like the average value is approximately 20% in porosity, the variability is pretty much the same, and so on and so forth. So we had some prior information, but nothing about the spatial distribution in the subsurface. So now we use the ensemble smoother multi-data simulation to update the models, and after just 4 iterations, this is what we get. Porosity is very accurate. You can see that all the gray models, they almost converge to the solution. So maybe we're even underestimating the uncertainty a little bit. Maybe there's a little bit of overfitting, but the solution is certainly accurate. For water saturation, the uncertainty is much larger. You can see that there's much more variability in the gray models in the water saturation domain than in porosity domain. This is because seismic data are less sensitive to water saturation than porosity. However, we can match pretty much what happens at the top. And if you look at, so the red line is the mean of all the realizations, and we do pretty well. We know that there's low porosity here, high porosity here, low water saturation here, high water saturation here, because there's this clay layer that is separates the two reservoir, and then again, low water saturation, and then we enter the water table. So it's still accurate in terms of the prediction. There's a larger uncertainty. So uh, we can do this for, now you learn the trick, you do it for all the traces. So here we get the posterior models for the petrophysical properties and here for the elastic properties. Now, most of the reservoir engineers, they use these models, they prefer petrophysical properties because they're easy to interpret. So here, for example, we can see that most likely there's one reservoir here, and then another reservoir here. And if you look at the water saturation, it looks like both reservoirs, they have low water saturation, which means potentially oil and gas. Um, then we have Monte Carlo methods. So in the previous case, the idea was we generate a bunch of models and we keep changing these models until we match the solution. Now here we do it one at a time. So we just build one model and then we try to match it and then we perturb the model. But the idea is that we use what we learned in the previous step in order to perturb the model in a smart way. This is essentially the idea of Markov chain Monte Carlo. There are some similarities between, for example, Markov chain Monte Carlo and ensemble Kalman filter or ensemble smoother. But here, let's imagine it as a sequential process where you generate a model, you decide if you want to take it or not, and if you take it, you're going to try to use this model and perturb it to get a better model. So this is the work by Leandro de Figueiredo. Leandro was one of my postdocs back in 2018. Now he has his own company. It's a startup called El Trace. They develop seismic in general, geophysical methods or software for oil and gas. And this is some of the recent research, which is the adapted delay of acceptance Markov chain Monte Carlo method, a really lengthy name. This is the research by Chuan Luo. He presented yesterday at the conference. So here you have a picture of him presenting his talk. So if you want to learn more about that, you can look at his publication. But the idea here is that the Markov chain Monte Carlo methods are generally slow. It takes a lot of iterations in order to converge to the solution. And now we have this massive 3D data set. It's going to take even longer. Sometimes it might take 2 or 3 weeks if you implement the original methods like Metropolis Hastings and so on and so forth. So we're trying to find some methods that can speed up the process and converge to the solution faster and represent uncertainty in an accurate or precise way. So now that we have looked at all the different probabilistic methods, what we're going to do is look at some examples in subsurface characterization. So we're going to start with oil and gas. We're going to look at CO2 sequestration, and then we're going to look at an environmental problem, which is the characterization of the critical zone. So this is a standard workflow that is applied in oil and gas companies. We have some seismic data, we predict elastic properties, and then we predict rock and fluid properties. The idea is that we can apply all of the methods that we look at before to this workflow, and we can estimate the properties of interest from the data that we measure. So this is again the example from Ming Liang, his publication in 2018, sorry. So here we apply geostatistical seismic inversion. Again, the idea was we generate a bunch of realizations, we update them using the ensemble smoother multi-data simulation, and we can do it trace by trace and compute the predictions for the entire 2D or in this case 3D model. You can also, it's generally hard to represent the model in 3D, but the idea is that most of these methods can be done trace by trace. You can actually generate all the models for jointly for the 3D model. For example, if you use sequential simulations, you can generate multiple 3D models with very efficiently using probability field simulation and so on and so forth. But typically the inversion, meaning the optimization, is done trace by trace. So you treat each trace independently. You generally lose a little bit in terms of spatial correlation because all the inversions are done independently at each location. But because of the continuity in the data, typically you see continuous models anyway. So ideally, we would like to extend these inversion methods to 3D optimization methods, but the computational cost is really large, so you have to find some way to make it parallel and so on and so forth. Anyway, here we did the Bayesian analytical inversion trace by trace. And so now for each trace, like every 25 meters in each direction at X and Y, we actually computed the probability distribution of porosity, water saturation, and so on and so forth. So here I try to map all the points where the probability of porosity being higher than the target of the company and the water saturation being lower than the target of the company is higher than 0.7. So this is an iso-probability surface, and all the points in the red area, they represent the regions where the areas where we expect the rock and fluid properties to be higher than the target that the company had. So in this case, it was porosity higher than 20% and oil saturation higher than 75%. So here, this is a similar inversion. This is the work by Leandro de Figueiredo. This is an isoprobability surface of high porosity, but this is a carbonate field. So this is probably the reason why you can see a little bit more segmentation. Maybe in this case, the target of porosity was a little bit too high, so the isoprobability doesn't look like as continuous as in the previous case. Well, so I talk mostly about oil and gas because oil companies have fantastic data sets that we can use to test our methods, but the same methods can be applied to geothermal reservoirs, hydrocarbon storage, and also CO2 storage. So the idea in CO2 storage is that we take CO2, for example, emitted by a power plant, we compress it at a supercritical state, and then we inject it in a borehole. And for example, we might use an aquifer of salty water or a depleted reservoir. So the idea is that we inject the CO2 in that layer, and then the CO2 will spread in time, but hopefully it's going to stay there if the permeability of the sealing layer is low enough. So that's I'm oversimplifying a little bit, but that's the idea of CO2 sequestration. But from the geophysical point of view, the physics is essentially the same. The only thing that changes, or the geophysical studies are essentially the same. The only thing that changes is essentially the properties of the fluid. Instead of having oil, we have CO2, which behaves differently from an elastic point of view, but we know the properties based on lab measurements and so on and so forth. So there are generally two different studies that you can do for CO2 sequestration from a geophysical point of view. One is the feasibility. So you want to find the ideal location where you want to inject CO2. So you want the reservoir to have high porosity and high permeability, but you also want the layer that is above the reservoir to have low porosity, low permeability to be a good sealing. And then you can also do monitoring studies. So what you can do is track the position of the location of the CO2 plume in time to make sure that it's not coming up to the surface or it's spreading in the direction that the engineers initially envisioned. So this is a case where we try to assess how valuable geophysical data might be to monitor the injection of CO2 in a reservoir. So this is a case, this is called the Johansen Formation. It is a case study in Norway. This is a deep aquifer underneath the Troll field, and this is the reservoir model that was developed by many researchers in Norway at SINTEF. So these are two publications by Egstad and Bergmo. So this is the permeability model. This is the porosity model. It looks a little bit weird in this kind of plot that I made because there's a fault here, so there is some discontinuity. But this is the injection well. So the idea here is to build a model where we actually model the CO2 injection and the displacement and the migration, and then we simulate the acquisition of geophysical data, and we see if with the geophysical data we can predict the migration of the CO2 that we pretend we don't know. So this is a feasibility study for seismic monitoring. So what we did is we ran fluid flow simulations, essentially, for CO2 displacement for 100 years. So we mimic the injection of CO2 for 100 years, and then we also mimic the migration of the CO2 400 years after the injection stopped. So this is a 2D section. The borehole is for the injection is here. So you see that the CO2 plume after 10 years, 60 years, 110 years. And so then every 25 years, we assumed that we were acquiring seismic data. And so we mimic what the seismic data would look like using seismic wave propagation models. So this is seismic in year 0 before you inject CO2. This is the seismic after 110 years when you stop the injection. And so if we take the difference of the two and we assume perfect repeatability conditions and no noise, so what we see is that there's an anomaly here, which most likely is the CO2 plume. So here, the goal was to show the value of the seismic data. So here we did the inversion without seismic data and here with seismic data. So this is the prediction of the CO2 plume and this is the uncertainty, which is the variance. And then here we have the prediction after 110 years and this is the posterior uncertainty. So you can see that the CO2 plume is much more defined and then the uncertainty is much smaller. You have pretty much zero everywhere with a little bit of uncertainty around the contact between the CO2 and water because there are some dissolution and so on and so forth. But the idea is that we can somehow track the CO2 plume. So this is the true model, the one that we developed using CO2 simulations. And this is the posterior model, the one that we predicted from the seismic data at that specific time. And this is just a representation of the uncertainty. So far I talked about seismic data, but the idea is that you can actually use multiple geophysical data at the same time. For example, we can invert seismic data and electromagnetic or electric data jointly. This is something that we do often in near-surface geophysics. We have refraction data for the seismic part, and then we have electric data. And we can combine electrical data and seismic data in order to predict porosity and water saturation with some adequate rock physics models. So for those of you who are not familiar, the critical zone is essentially the first 30 meters in the subsurface, or 100 feet. It's where the rainfall infiltrates in the rocks. It creates some flow paths. That's where the roots of the trees propagates, and so it's called the critical zone because it's responsible for the development of the ecosystem. Now, the Blair Wallace site is one of the most studied from the geophysical point of view. It's 10 miles east of Laramie. We have several 2D section lines of either seismic or electrical data and some lines where we have both data sets. We also have some boreholes drilled by either USGS or University of Wyoming. This is the PhD student of Brady Flinchum, who is now a professor in Australia. So here we have different rock types. So the first 30 meters in the subsurface or in the critical zone, we typically have some really unconsolidated rocks or disaggregated rocks at the surface, and then we enter into what we call the fracture bedrock, where you have bedrock which present fractures that are due, for example, to, like in the Blair Wallace, frosting and cracking, and then you have the fresh bedrock, which is not weathered. There's no weathering processing yet. So here we have to build 3 different rock physics models for each of these rock types. Anyway, this was what Brady did in his PhD. He took all these seismic and electrical sections. He computed P wave velocity and resistivity, and then he converted into porosity and water saturation. Now, the interesting thing is that he did it for different sections with different orientations, some that were perpendicular to the stream, to the creek, and then some that were parallel to the creek. And then you can see that there are great variations in terms of porosity. For example, here in cross-section E, here the high porosity layer is very thin, and then here instead it gets much larger. So this might be due to tectonic stress or regional stresses and so on and so forth. So using these maps, he was able to do some interpretation about the thickness of the saprolite, the weathering in the bedrock, the depth of the unweathered bedrock, and also the distribution of the water. So here there's a conceptual model of how the critical zone looks like. So what Brady did was to build maps with the saprolite thickness, with the depth of the bedrock, and then the water holding capacity, which is the property that we're trying to estimate because we're interested in the water volume of the aquifer. So um, the idea here is that I show you different examples where you can apply geophysical inverse problems. My research focuses on understanding the petrophysical behavior of the subsurface, either for deep reservoirs of oil and gas or CO2 sequestration, or shallow critical near surface layers. So the research can be applied to CO2 storage, groundwater, but it could also be applied to natural hazards and environmental studies. Every time we have some geophysical data, we can apply an inverse method as long as we know the physics. So the goal here was to improve the accuracy and quantify the uncertainty in the model predictions, which are really important for the stakeholders to make informed decisions about the exploitment of natural and energy resources. We want to provide these models to oil companies such that they can drill safely and maximize the outcome. And then we can provide these aquifer models to the stakeholders in the state of Wyoming such that they can make informed decisions about distributing the water for agricultural purposes. But the general idea is that we don't provide a single model, we provide a some sort of measurement of the uncertainty such that the stakeholders can make more informed decisions. They know how much they can trust our models. In some cases, our models could be really accurate and really precise. In some cases, the precision might be relatively low. And so we want to warn the stakeholders that these models might carry high uncertainty. So finally, before concluding, I would like to thank my current and former students, Kristen, Wenting, Minliang, Smith, Chaojeng, Mohit, Peng, Leandro, Mateus, Jorlivan, Chuan, and my current student, Asa Glauco and C. New. My former students have gone to work in different companies and academia, and they're having great careers. But they're really the reason why I'm here. If I'm receiving this award today is because of them. They're doing the work. I just have the privilege to go around the world and present their research. So thank you very much. And if there are some questions, I'm happy to answer.